Okay, recording is started. So, good morning, students. This is a class of geotechnical engineering. So, we are discussing about permeability of soil. Uh, we have started discussing from what is permeability of soil, about Darcy's law of permeability. Okay, and seepage pressure. Okay, seepage pressure or actual discharge or theoretical discharge. All these things are already discussed. Factors affecting permeability also is discussed in the last class. Yeah, today we'll discuss about stratified soil. Okay, so in the last class, if you remember, we have I have mentioned about stratified soil. So what is stratified soil? Stratified soil is a kind of a layered soil. That means it is a combination of individual soil layer having individual index property or soil property. That means each layer have different or individual soil property. Okay. Okay, first let me share my screen first. Okay, my screen is visible, right? Okay, okay. Okay, can you see this? Okay, so about stratified soil that I already mentioned to you. So here I have taken this screenshot from a book of soil mechanics and foundation engineering written by BC Punmia. Okay, so here you can see in nature soil mass may consist of several layers deposited one above the other. Okay, so I've already discussed to you that soil in actual site or in nature the soil exists in different layers. Okay, so their bedding planes may be horizontal, inclined, or vertical. Each layer, assumed to be homogeneous and isotropic, has its own value of coefficient of permeability. So about homogeneous and isotropic, I think you already got this thing in basics civil engineering. Homogeneous means what? Made of same material. And isotropic means what? Have property or elastic property same in all direction. Or you can say having elastic property constant in all three mutually perpendicular direction. It's called isotropic. Okay. So individual soil layer have its individual soil property along with coefficient of permeability. So when we have discussed in the last class about factors affecting permeability, we have discussed in a stratified soil, coefficient of permeability, that is average coefficient of permeability, is depend on the direction of the flow of the water. That means uh, if the direction of the flow of water is parallel to the bedding plane or parallel to the layered soil or parallel to the stratified soil deposit, then the particular coefficient of permeability or average coefficient of permeability, say suppose K1, and say for us when the flow of water is along the perpendicular direction to the stratified soil, then say the coefficient of probability is K2. So this K1 and K2 may not be same. Okay, that means the coefficient of permeability is depend on the direction of flow of water, especially in case of stratified soil deposit. So in that case, we can have two cases when it comes to determine coefficient of permeability for stratified soil deposit. Okay, so here you can see the average permeability of the whole deposit, that means the whole stratified soil layer, will depend upon the direction of the flow with relation to the direction of the bedding planes. Okay, so we have considered both the cases of flow. That is, first case is what? Your flow is parallel to the bedding plane, and second case is your flow perpendicular to the bedding plane. So for these individual two cases, we can determine the coefficient of permeability for stratified soil deposit. Okay, fine. So here, I think you can see this image. This image also taken from that soil mechanics and foundation engineering by BC Punmia. Okay, it is in a page number 196. Okay, so you can also refer different books, not a big deal. So here you can see two cases are given here and some derivations are given here to find finally the kx, and here you can see kz. Kx and kz are what? Kx and kz are average permeability or average coefficient of permeability in case of bedding, in case of stratified soil, depending on the direction of the flow. Okay, so here case 1 is what? Average permeability parallel to the bedding plane, and case 2 average permeability perpendicular to the bedding plane. Okay, so what is the difference between these two cases? Here you can see from the diagram itself, you will have an idea. Okay, so here you can see this portion is suppose considered, you can consider this is a stratified soil having different layer. Say this is layer 1, layer 2, layer 3 up to layer n. Okay, so this is a stratified soil. Okay, so first we'll discuss about average coefficient of permeability parallel to the bedding plane. Fine. So here you can see this stratified soil layer is fitted or sandwiched between two overhead tank on this side, left side, and on the right side. Okay, and if you can see closely, this the overhead tank on the left side, it is little bit higher, at little bit higher elevation compared to the uh, the water tank fitted on the right side. Okay, so here you can see small h, you can see this small h represents the head, or you can say hydraulic head. Because of this hydraulic head, or because of this head difference, water flow from higher gradient to lower gradient. So water will flow obviously in this direction since this elevation is higher than this side. Okay, this is a very basic things, you have to know these things. Okay, so assume some amount of water is allowed to pass through this overhead tank, and water will pass through it. Okay, because of the gradient. Okay, fine. And the discharge coming per unit time, say it is denoted by small q. That means small q amount of water coming per unit time through this soil, and it will cross through it like this. Okay, now for this soil layer, individual soil layer, assume z1, z2, z3 up to zn are what? Thickness of the layer. Okay, here you can see, let z1, z2 up to zn are considered as the thickness of the layer. Okay, this thickness, and k1, k2 up to kn are considered as a permeability of the layer. That means this k1, k2, k3 and up to kn are individual coefficient of layer, sorry, individual coefficient of permeability for this individual layer. That means k1 is a coefficient of permeability for layer 1, k2 is a coefficient of permeability for layer 2, and so on. Okay, since now it is stratified soil, and that means they are all together, we need to find out the average coefficient of permeability. Okay, now in this case, since water is flowing in x direction, suppose this consider is x direction, horizontal direction is represented by x direction, and perpendicular direction represents by z, that is z direction. Okay, now in this case the water flowing in x direction, so let's consider kx. Okay, kx is the average coefficient of permeability or average permeability of the soil deposit parallel to the bedding plane. Okay, so we need to find out this kx for this case 1. Our main aim to find out the average coefficient of permeability parallel to the bedding plane, which is denoted by kx. Okay, but we know the individual k. We know the individual k, k1, k2, k3, kn. Okay, so how to do? Now here you can see when the flow is parallel to the bedding plane, we can first consider, we need to consider that hydraulic gradient. Now what is hydraulic gradient? H by L, that is head difference divided by the length traveled by the water, H by L. Here you can see, for flow to be parallel to the bedding plane, the hydraulic gradient I will be same for all the layers. Now here you can see, H, this H will not going to change throughout the flow of water. And what is the L? Where is L? L is what? The length traveled by the water. Now since water flowing in this direction, so length traveled by water will be the length of this layer. It is not showing here, but suppose you can consider, say, L. Capital L you can consider. Capital L is the length of the soil layer. Okay. So what is the I? Hydraulic gradient for this case? H by L. And it will remain same for each layer. So since H by L remains same for each layer, we can say hydraulic gradient, that is I, will also be going to remain same for each layer. Like I for first layer, second layer, third layer, or all the layers will be same. The value of I will be same, H by L. Okay? Okay, so I will be going to be same. Fine. Now, yeah, what is written? I will be same for all layer. However, now see, however, since V is equal to Ki, okay, now we know as per Darcy's law, Q is equal to Kia and V, that is discharge velocity or Darcian velocity, small v is equal to K into I, that is coefficient of permeability multiplied by hydraulic gradient. We know this formula. Now, since for each layer, the value of K will be different. Okay, now you know that for each layer, K will be different. So we can say, even though I is constant for each layer, but since K is different for each layer, so we can say velocity of flow, that is discharge velocity, will also be going to be different for each layer. So say, that's why it is written V1, V2, V3, Vn. Okay, so for each layer, the velocity flow will be different. Okay. Since V is equal to Ki and since K is different, the velocity flow will also be different in different layer. Got it? यहाँ तक ठीक है? Now it is already mentioned here. Kx, let's say Kx is the average permeability parallel to a bedding plane. Now we can consider the first equation is what? We know that total discharge through the soil deposit is the summation of discharge through individual layer. Now since Q amount of water is entering in the soil element within a time, okay, this must be equal to the water coming out, isn't it? So we can say, let's say Q1, Q2, Q3 up to Qn are the unit discharge. Q1, Q2, Q3 up to Qn are the unit discharge passing through the individual soil layer. Okay, so say Q, that is total amount of water entering the soil element, that is small q. Okay, it is can be equal to summation of Q1 plus Q2 up to Qn. Okay, it is very simple to understand, right? Okay, so in place of Q, we can write as per Darcy's law, Q is equal to Kia. Kia. K is your coefficient of permeability, I is your hydraulic gradient, and A. It is written as Z, but still now we know what is it should be A. Okay, A is what? Cross-sectional area of the soil element perpendicular to the flow. Okay, you know Q is equal to Kia. Now here if you see, this is a two-dimensional soil element and we have considered the thickness of the layer. That means I will show you here. Wait, let me take one color. Now if I consider this kind of thickness, oh sorry, okay, whatever, so this thickness is taken as 1. Okay, can you understand? Okay, so you cannot see the thickness here. So for unit thickness, considering unit thickness or unit 1 unit of thickness, when you find out when we need to find out the cross sectional area, what will be this? Z multiply by thickness, and thickness is written as 1, and the total thickness of the layer is represented by capital Z. total thickness of the layer is capital Z, and Z is a summation of Z1 plus Z2 plus Z3 up to Zn. Okay. Now, this for Q1, discharge through layer 1, Q1 can be written as KIA. Now, in for layer 1, K represented by Kx. Hydraulic gradient I is same for all layers, so I only. And in place of A, we write Z in Z1. Here you can see I'm talking about this one, Z1 into 1. Okay, Z1 into 1 represents cross-sectional area. Okay, similarly for layer 2, KIA, Q is equal to Q2 is equal to KIA. Now, in for layer 2, K2 replaced the K, hydraulic gradient is same, and A, area for the second layer, the cross-sectional area will be Z2 into 1, that is unit thickness, so only Z2. So it will go on. Okay, and for average discharge, for this consider total soil layer, if you consider, this Q will be represented by same KIA. Now in place of K, we write KX, which is represented by average coefficient of permeability for this whole stratified soil. Kx multiply the hydraulic gradient I, since I is constant for each layer, and capital Z. Z is your total thickness of the layer. Okay, so it is very simple to understand this. Now we just need to simplify this. After simplifying this equation, we can find out the value of Kx. We can find out K1 plus K2 plus K2, sorry, K1 plus Z1 plus K2 plus Z2 up to Kn plus Zn divided by Z1 plus Z2 plus Z3 up to Zn. And this represents Z, that is total thickness of the layer. Here it is written. So this is a formula for coefficient of permeability for uh, flow through stratified soil in parallel to the bedding plane. Okay, this is a formula that you need to remember. Okay, some problem may come in exam and maybe okay, different or what is constant in parallel, you have to know these things. Okay, so for flow parallel to the bedding plane, Kx is given as K1 plus K1 Z1 plus K2 Z2 up to Kn Zn divided by total thickness of the layer. Okay, so this is a case 1. Okay, and regarding case 2 we'll discuss in next class. Okay, but you can, I'll just give you one just one difference here, almost similar to that case 1. Only different, you can see the drawing, the overhead tank is fitted at the top, not at the side. Okay, but in this case the hydraulic gradient will not going to remain same for each layer, and but velocity of the flow will going to remain same. Okay, this is only the difference. Okay, when the flow is perpendicular to the bedding plane, hydraulic gradient will going to change, will be different for each layer, and but velocity of flow will be same for each layer. This is the difference between this case 1 and case 2. Okay, you can try to go through this case 2, try to understand these things by yourself, even though I'm going to discuss this in the next coming class. Okay, got it? So this is all about today class. I'm just trying to close my sharing now. Okay, so try to understand these things once by yourself. If you don't understand, I will discuss these things in next class also, so don't worry. Fine, is it clear to you? So let's take the attendance then. Okay, fine. So first I'll just stop my recording then.